Welcome to this morning session. Our presentation is Losev from Yale, and he will speak about category O and Harish-Chandra bimodules for quantum groups at Losev.
Welcome. Thank you to the organizers for having me. It's great to be here. So this is based on my older work and newer work by Trung Vu, who's my student, and was going to build the job market. Not sure why I mentioned this before. So the plan is the following. I have two categories written here: category O and category of Harish-Chandra bimodules. And I want to explain what they are for the classical algebras. Then I'm going to explain what the categories are for quantum groups. And finally, I'm going to state some results that are going to be category equivalences between this category and yet another. That's the plan. So let me start with some notations. Capital G is going to be a simple algebraic group. Over a field F. And at this point, the only thing that I need is that the field is algebraically closed. Inside, I will consider the barrel and the maximal torus in the usual notation. And then I can look at the real algebras. For no G's and small p. Okay. So then I'm going to consider the following categories. The first is category O. And what it is going to be strongly be equivalent, and we'll explain in a minute what this means. Finally, generated huge modules. And strongly be equivalent means the following thing. It means that I have a rational reaction on my moduli. And I wanted to satisfy two conditions. So it's like that. First, I want that the structure map, which in terms of M to M is the equivalent. This condition is known as a weak equivalence.
Enough to take G tensor as well.
G tensor I can do.
No, it's not for that to be B equivalent.
Yeah. Oh, yeah. And then the second part of the condition is the differential of this B action is the same as the action of B viewed inside U. Okay. So if my field is characteristic 0, then it's the same as to say that Cartan has diagonalizing this integral eigenvalues, and maximal importance of algebra has locally independently, and in characteristic P I need to apply it. Okay. So that's the first category I'm going to consider. The second category are the category of Harish-Chandra bimodules. is going to be the category of weakly equivalent, or G. Finally generated right in G modules. And why are they called bimodules? That's because there is a unique commuting left axle. With the property that the differential of the action was zero. Is the adjoint, which means that I send some element B in my bimodule to X B minus. Okay. So this guy is harmonically bimodules. Now to remark I model, first is that these categories are quite closely related. So the relation between them is the following. So I'm going to consider so-called Harish-Chandra symptom, which by definition is the invariance of the group inside the algebra. Let me call this capital Z. And inside, I'm going to consider the maximal ideal of all elements which are trivially or which end by zero on the trivial representation. Then I can look at the subcategory, which I will call HC0, inside of HC, consisting of all objects where M0 acts by zero observers. Okay, that's a full subcategory. And I have a functor going from HC0. Well, maybe I will want to write categories here. So B HC0 to D O. And this functor sends B, the derived tensor product of this B over U0 with delta 0. So where U0 the quotient of UG by this M0, and delta 0 is a Werner module with high spacer, defined as G owned by UG. Okay.
So your notation is a little confused. You are taking HC0 equals B in HC,
Yeah.
but B was a body.
No, Harish-Chandra category.
That's good point.
No. No, I understand. That's the object. Okay.
Right, so I got this functor, and the claim that this functor is equivalent. And moreover, if characteristic of zero, characteristic of f is equal to 0, then this functor is T. Okay. It restricts to equivalence of abelian categories. So not only the equivalent as derived categories, the equivalent as abelian categories. But in characteristic P, you only have derived.
That's according to something, right?
Yeah. Okay. A second remark, so let's see, hopefully it will be visible if I write about this line. Second remark is that if the characteristic of my f is equal to p bigger than the Coxeter number, then the principal box of this categories, and principal just means that this M0 acts on the left with a generalized eigenvalue 0. So previously I required almost eigenvalues, so I want generalized. Maybe I should say on the left locally. So the principal blocks are in fact derived equivalent to something called the affine category. And I will later on explain what this means. But for now, let me just tell you that this is kind of a model category in this business. And it's a golden standard of category. And this is a result of the coupling of Risch. And myself. And the way how this is proved, and for example, how this derived equivalence is proved, that's an order for experts. So proved using visual coupling of Merkel-Ricci remaining and derived optimization. Questions?
So you said the principal block, is it a single block?
Yep. That's a block of what you call trivial.
The block of the triple. Okay.
So this conference happens to have quantum groups as a title. Let's talk about quantum groups. And let's start by talking about the solvents themselves. So certain algebras. So how does the story start? Well, we have like U VG defined over the field of rational functions in the determinant. That's a different Jumbo quantum group. And I want to consider its forms over C, where I specialize D to some complex number Q. So Q here is a non-zero complex. So what I need to do, I need to choose a lattice inside of this algebra. And what I get is and then specialize. Inside of the lattice. And there are three natural choices for this. There is a most naive one, which is called the continuity cuts. DK form. That's the most naive one. So this one is generated by the usual generators, which are EIs, FIs, and K lambdas, where lambda lies in the labels. Okay. Then there is a so-called Lustig form. And this guy is generated by the divided powers of E's and F's, and also K lambdas, where L is a positive integer, and Q is the divided power. So di L square brackets is di power of L divided by quantum factorial of L. In the notation is this L sub di factorial means it's as quantum factorial for v to power di, and di is ratio of lenses of terms. For short roots, it's equal to 1. Okay. And then there's an intermediate form, so-called mixed form. Which I will call, so Lustig form, I think I will call super L. And this form will be called QQ mix, where I only take divided powers in the E's. Like Fi, of L, Fi, and K. Okay. So these are three forms that I'm going to care about. Let me explain some properties. So first, notice that all the algebras, so UQ, which potentially transform, UQL, and UQ mix are graded by the root maps. So which are involved by for example, PI has degree alpha. Okay. Second, on the level of lattices, I have inclusions, and then they give me homomorphisms between the algebras. So I have UQ mapping to UQ mix, mapping to UQ Lustig, and those guys are either isomorphisms if Q is not the root of U. Okay. Because if Q is not the root of U, it is a quantum factorial is not. Number 3 is the following sort of intuition, which also suggests what kind of questions we can study about this algebras, is that if U is a piece root of unity, where P is some positive integer, then if U becomes drafty, like the universal enveloping algebra of G over F P bar, was that P bar only makes sense when P is prime, while Lustig behaves roughly like the distribution algebra of the group G over. Okay. For this analogy, P, strictly speaking, is P prime, but for quantum groups, it really shouldn't matter with the order of Q is prime. Okay. Questions?
Yeah, can you spell the distribution algebra?
It's like, you do the same thing, but with U of G over the ratio. You define a similar integral form and reduce much, and then this is realized as functions, as functionals on f of G is applied one. Well, that's distribution algebra. So, more questions?
So this notation, this one is the distribution supported at one.
Yep.
Yeah.
So these two are the same when you're working over an Archimedean field, right? The
Characteristic.
distribution one on the group and the enveloping algebra.
All the same with characteristic zero
Yeah.
for any
That's
reasonable
right.
time.
Yeah, yes. But
And characteristic zero is a characteristic of the of the coefficient.
Sure, I have a question about behaves roughly like, it's more like analogous to. Because you can iterate Frobenius in the rational category,
That's right.
Yeah.
and, it's much more complicated.
It's complicated for more complicated for some questions. It's easier for some others.
You don't know what the irreducible representation. Term or something. You're doing the monomies.
Excellent, Ross. So, based on this property 3, it makes sense to ask about the action of UQ on UQ.
Yeah.
So, we indeed have that right action. Of UQ of UQ. But in the usual conventions, this only happens if U is an order document. So for various structural purposes, the case of even roots of unity is more complicated. But with Trung Vu, whom I already mentioned, and Sasha Tsymbalov, we propose some modification of UQ and UQ-heuristic. So that we still have this action and many other nice properties. So that this algebras behave uniformly.
So for G2, don't we need to avoid 3?
Yeah, I need to.
Yeah.
I need to prime to 3. But there is this fix, which fixes this all. It's kind of technical, so I'm not going to explain it, and I will resolve the issue of even versus odd roots of unity by ignoring this issue. Okay. It's just kind of technical. So let's see that I will need E7 subalgebras in UQ. And the subalgebras are going to be the Harish-Chandra center. which I define as invariance of UQL inside of UQ. This is a subalgebra central. And then I will have the guy which I denote by UQLF. LF is from locally finite. And so what this is, it's called elements in UQ such that they lie in a finite dimensional subspace with a joint representation. Okay, that's also a summary. And the way to think about this is that, again, what you are some technicologists, UQ already quantizes functions on open Russell. And UQLF quantizes functions on G.
Sorry, can I? So you said that we have uniformly for all, I'm a little bit behind you. So UQL and UQ we have uniformly. In what? Can you make it a little bit more concrete?
For example, let's see. You have the uniform behavior of Frobenius center, which became functions on suitable kind of Langlands dual. For example, in the usual setting, you need to put some technical modifications. There are some issues with Harish-Chandra center, which now behave uniformly, and so on and so forth. So typically, if you look at the literature, you will find a bunch of results for all the roots of PhD, like classical work of the Conchini-Cast and Braccesi.
Yeah.
And then there are some more technical versions for even roots of PhD. For example, there is a work of Tanisaki describing the Harish-Chandra center. This gets more technical in the usual sense. So what I'm saying roughly is that you can add more technicality on the basic level of definitions. So these modifications, they can the generators and relations look ugly. But thanks to this ugliness, you get really uniform descriptions.
So same generators, more relations, what?
The generators are similar. Maybe we can talk about this later. Okay. All right. Since I have many questions, I will let myself find it. Okay. So this was about algebras. Let's now talk about categories. And let's start with category O. So to begin, let me fix the following notation. I'm going to take, that's not a face, it's an invariant form. On Q, such that the square of a short root is equal to 2. And then, okay, I still have this little piece of work to define what U per Q is. And as by definition, let's say Q graded finitely generated UQ mixed modules, we call them M, such that, well, M is graded and I require that K nu acts by U to power lambda paired with mu, which thanks to my conventions is an integer, all n lambda. Okay. If my Q is not a root of UH, this specifies n lambda uniquely, but when Q is a root of UH, the scalar doesn't determine bound. Okay. So that's the first condition. And the second condition is that the weights meaning lambda such that lambda different from 0. So the set of weight is bound in the usual. Okay. So that's the definition of quantum category O. Other questions?
You need to encourage like EI and lambda, is it and lambda just alpha?
So that's what I get when I say it's graded. So my algebra is graded, I consider graded modules over the graded algebra. That's a category O. And then the category of Harish-Chandra bimodules, HCQ, is defined more or less in the same way as before. So it's defined as VP equivalent, VP UQL equivalent, finitely generated right modules over UQ locally defined. Okay? With the condition that the action of UQL is rational. Okay? So I don't get some nasty representations like UQL itself. Rational will mean locally defined. Action is rational. For example, the following lies in this category. For example, if V is finite dimensional, rational UQL rep, then V turns out ULF is an HCD. Right? So this has an obvious structure for right module, and it has diagonal action of UQL. Okay? It satisfies the conditions. And similarly to what happens in the physical setting, these guys are actually bimodules also. One can write down the action. Right, other questions?
Well, you could have chosen the other mix, the other way around, where you divide the S but not the Is. Since you make a choice from direction, that will give different category.
Yes. Although maybe the thing.
No, but the carbon evolution will change one to the other.
Yeah,
But
Yeah.
but the value evolution doesn't have to mix any.
right, but it kind of it sends one mix to the other.
Yeah. Exactly.
So this is just ripped off from the classical definition, right? In the classical definition, I want the action of Borel, meaning I want the action of this distribution algebra, and distribution algebra corresponds to divided powers in the root batches of Schleier's power. But geometrically, it's more natural than the algebra. Right? So now, let me get to main results. So what do I want to study? Let me take epsilon is L through the infinity. I want to assume that L is odd and L is bigger than the positive number. Many of the results I'm going to talk about hold when some of these assumptions are removed, but they become more technical and partly not yet finished. So I want to consider the category O epsilon, and I want to consider the category HC epsilon 0, where this guy are all, I'm going to get in trouble. All bimodules such that B M0 0 and M0 is defined in the same way. So M0 is the Harish-Chandra center. It's a maximal idea of annihilating the trivial groups. And I want to concentrate on principal blocks. Let me have the notation for them. It will be O epsilon 0 on the left with a hat, and HC epsilon 0, 0 on the left with a hat, where this, for example, means that M0 at slope region. So this is a category that I want to study. And I told you that the classical counterparts in characteristic P are derived equivalent and equivalent to the affine category. And this is the result that I want to have. So now I need to explain what the affine category is. And for this, I will need a bunch of varieties and schemes. So let's see. I'm in trouble. Let's say both phase B is going to be the phi variety. The variety of all Barat subalgebras. Then I'm going to have G tilde, which is growth index resolution, and inside of it N tilde as Springer resolution. So G tilde is all pairs B F's involved with B times B. So X is in B. And N tilde is very similar. But now I require that X lies in the derived subalgebra. So these three guys are smooth varieties. And then I have Steinberg, which is the norm reduced. So this is G tilde times G is N tilde. And so what this is explicitly, it's a scheme of triples. U1 into F. Size of X lies in U1. Intersection with U2 derived such. Okay. So now theorem in preliminary form. So the first part is due to myself, 1, 2, 3. And it says that the principal block of category O is derived equivalent to dB Koch G of Steinberg. And the second part is due to Trung Vu in 26. Says that this category of Harish-Chandra bimodules is also derived equivalent to the things. Okay. And this is my affine technical. Or at least one version.
So the right hand side is not sensitive to epsilon.
Yeah. That's it. A couple of comments. So in characteristic P, more or less from the first principles, which is this BMR localization theorem, we know derived equivalence between these two. And then with some work, one establishes the derived equivalence of one of them, this Dibikov geostack. In quantum setting, derived equivalence between these two comes as a consequence. So what kind of happens is the geometry is screwed, which is a disadvantage of quantum setting over the classical setting. That's what I meant when I answered that question, that sometimes classical things behave better in some respects. And so basically geometric arguments don't work, or at least I don't know, and I don't know anybody who knows how to make them. So instead, I will use alternative arguments, and I will try to explain it maybe in the last 10 plus epsilon minutes. What goes into kind of the proof of the equivalence in the bottom. So techniques are sort of related for both of these equivalents, but they're quite different. Before I get there, are the questions?
So this theorem is true classically also, right?
Yeah. But classically, you just use the localization theorem and then you're done.
Yeah.
While quantumly, one would hope to get a localization theorem out. Nice.
Is there any connection to the ABG picture at all? Is
Second?
there any connection to the ABG picture?
ABG, which is article of the Republic of Ginsburg. That's a good question. I need to think, but I would somehow say not really.
Okay.
It's kind of, kind of more is a rational representation, kind of representations of the mystic form are sort of much easier than this thing structure.
So can one go directly? I mean, these two objects are isomorphic with one object. So
You mean vertical equivalence?
yeah, right.
You don't even write a function.
That's what I was asking.
You can write a function the same way as before, and it's some from this equivalences. They kind of, if one works hard enough, which I hope my student will, then one should be able to prove that the equivalence is given by the classical form. But so far, I wasn't quite there yet. So some ideas of proof. And mainly, this is a direct equivalence. Perhaps one should try to understand what happens with these structures. And one should try to get an abelian equivalence, and in fact, this is what is proved. So we want abelian equivalence. And for this, I need to recall some construction due to this lookup. And that's a construction, so ingredient one, so-called non-commutative Spring-Berg solution. Which is due to Bezrukhavnikov and is written in Spain with Mirkovich. So what is the non-commutative spring resolution? So that's a certain algebra. It's an algebra. A, and this algebra is really over regular functions on G tilde, which is CLT, and there is CLT, C2W. It bears an action of G. And it's flat. Well, it's flat over C of T and it's flat over C of T separately. I will withdraw it. And then I'm going to specialize it to 0 here. So I'm going to consider
So
0.
Teacher. What is teacher?
There are no checks over T. It's just T.
Oh, it's just T.
It's just German T.
Oh, okay.
So this is recorded. You should send a link to Katarina Strauss. She likes me. You should send a link to Katarina Strauss. She likes my German letters.
Ah.
So then I base change to the 0. I call this piece. So this is an algebra over C of t. Okay. So this algebra that I'm not going to define. Definition takes some time. But why we care is that because this modules over this, say over A, is derived equivalent to coherent shift over G2. And this is what makes it a non-commutative resolution. I will need G equivalent version. So
I forgot what's this here.
this is a
Easy one.
let me write it in a little less mysterious. So, one knows after Bezrukovnikov that the right category of G equivalent A modules is equivalent to dB of G of G tilde, and the right category of A0 module G. Maybe let me write A0 op here. Doesn't matter for the statement. Is equivalent to dB of G of N0.
So you're saying there is some A.
Yeah, which is constructed in a certain fashion, and I can explain it to you later.
Okay.
Which makes this one.
Satisfying these two properties.
So you have a certain vector bundle over G tilde, and you take this and the box. And this sort of combines these two things together and get a version for the Hecke. So more or less the consequence of this is that dB of the following. So I take A, I tensor it over C of G, is A0 opposite on G. So this is going to be equivalent to dB of G of state. I kind of take this product, the product of these two equivalents, we pull it back to strength. So a precise theorem due to Vu in 26 is that my category of Harish-Chandra modules as an abelian category is equivalent to this. So A times the 3G mod. And this is what actually is being put. My time is up. I somehow requested myself 5 minutes.
2 more minutes.
2 more minutes. But you know, it's kind of it's a talk is a show, and in a show there should be some advertising, right? Yeah, that's how it works, and I need to advertise my student. Right? So let me very briefly say how this is proved. So the proof is long and difficult. So there are 2 ideas. So first, one constructs full embeddings from the same category to here, and the category is going to be the category of circle modules for the affine value. The smaller circle. And these are full embeddings. That's the first step, which takes long. It's not immediately clear how to do this. And then what one can show is that both these categories have enough projective.
So do you mean CG height or CG there? In the top, yeah.
CG.
Oh, CG, okay.
Yeah.
But A1 is CG height module. Okay, so now you think of this as a CG module. Okay.
And so then, so there are enough projectives. And what one can show is that these categories of projectives so under this full embeddings, the categories of projectives lies like in the image, and what they kind of correspond to. Oh, it's like equivalences. They correspond to the part of this category of sorted modules corresponding to the lowest 2 sides. So this is an additive category whose intercomposables are labeled by the elements of the affine algorithm, and I look at those objects which correspond to the smallest 2 sides. And then I have this equivalence of categories of projectives and then more precise my unit. Okay, good. That's it.
Questions?
I have a very long question. Is the weak form appears somewhere in the top, or is it just provisional?
The mixed form appear to define the category O.
Because basically you want a B module, but capital B, like the curve.
So my classical category O was a what? They were modules over G and modules over B in a compatible sets. I can say as follows: I take graded modules over G, which are additionally modules over the distribution algebra of N. Okay, and distribution algebra means divided powers. And so in the quantum definition, I just directly insert divided powers into set.
So in this theorem of Bezukhov-Nekov, which is still there at the top. So of course, N today is a sub variety of G today, right? But on the left side, you have, in one case, you have a module, and another case of the opposite a naught module. That looks a little bit kind of strange to me that on one side, you have a module and on the other side it becomes, I mean, it's a question of left and right, of course. But I don't see that on the right side, how that left changes to right.
So, so I told you that my A is an homomorphism algebra of some vector bundle with certain properties. The dual vector bundle will have the same property. The dual vector bundle will have the same property, and of course, the homomorphism algebra of the dual is a whole. So I can write it without opposite here. But
But you want it here. You want
yeah, so the T structure will depend on whether I have A or A. And for the correct structure, I need to have.
So in that theorem, you could have replaced op with the A naught instead.
That's it.
Yeah, okay, that clarifies.
The mixed form appears naturally because it's the Drinfeld double of the Borel and you get non-degenerate. So the place you're all in,
No,
it doesn't mix form.
no.
Because if you don't do mix, then you won't get non-degenerate very. So
Right, but somehow it never appears explicitly.
never.
Yes.
Sorry, I think you mentioned one point. Could you remind me about the dependence of the other of the one time, right?
Or absence of such, that's right. It's not, it's independent.
So this.
So sorry, kind of, guys, I have a few questions. Please.
So this calculation of whole mixture doesn't depend on the.
Right, that's kind of, so the way how it happens is the problem. So you have this various L's, and you have the full category O, which is kind of sum of various blocks. And the blocks themselves are independent of the root of unity when you ensure this parameter. For example, when you are odd and for prime to 3 for T. What does differ is how many of each block you have. For given F. So kind of this the categories won't be equivalent unless I restrict to principle. And if my if the root of unity if the order is too small, then I have more singular versions.
Can I ask one more question? I mean, maybe not directly related, maybe. So does one have a good understanding of center of the Concini cos quantum and root of unity?
Yeah.
Does one have a good handle on the center of that?
Yeah, so if your root of unity is kind of odd,
Yeah, no,
then it goes to the Concini cos and Pachete.
Yeah.
And then with our version of the quantum group, we have a uniform description for even and odd.
No, I'm happy with the R. So in the R case, what you're saying?
So you have this like welcome zero, right? You have the Frobenius center that you understand, which are basically functions on the open glass cell.
That's right.
You have Harish-Chandra center, which is
Correct.
and then they map to the same thing,
Yeah.
and you take the five apart.
And that's exactly the center?
Yeah. That's it.
I thought that the center is bigger than that. No.
Well, again, so if you're in the original setting, you will need to kind of replace the functions on the open glass cell by functions on a certain cover. So in this sense, it's bigger. In our version, this cover is being eliminated. Yeah, that's what you. If you look at the continuing path paper, that's what it is.
If there are no questions, that's like what?